took page 569 last night. We had questions number 1 and 2, 4 to 7, 9 to 12. Any of those that we need to go over, please? 10, 5, 10, 4. Okay, we got 4, 5, 10. Any others? 12? 4, 5, 10, 12? It's in the back of the book. Yeah. 11? I get 4, 5, 10, 11, and 12. Let's take a look at number 4 right now. 4 says, at a point in the Earth's atmosphere, the electric field is 150 newtons per coulomb, downward, and the gravitational field is 9.8 newtons per kilogram downward. What's the electric force on a proton at that point? What's the gravitational force at a proton at that point? Sometimes it's helpful to draw it out. If in doubt, draw a picture. Okay. A worst case scenario is it's not going to help you, but it's certainly not going to hurt you to draw a picture. So draw a picture of the Earth here. We have a point up here somewhere, certain distance away from the Earth. We don't know what that distance is. We know that at that point, the electric field strength is pointing downwards, and it has a value of 150 newtons per coulomb. And we know that at that same point, we have a gravitational field pointing downward, and its value is going to be 9.80 meters per second squared, or newtons per kilogram, sorry. We're going to find the electric force at this point. So let's ignore the gravitational field right now and look only at the electric field. We have an electric field pointing downward at that point. What do we know more about, the producer or the experiencer? Well, we know something about both, right? If we look on our data sheet, we can get the mass of the Earth. If we look on our data sheet, we can get the charge of the proton that's placed at that point. We know something about both the producer and the experiencer. The one thing we don't know is the distance away from the producer. We don't know that value. So if we don't know how far away from the producer we're trying to find the field strength, then, or that we have the field strength for, then we're going to have to use the experiencer equation. Okay, we know that the Earth is the producer. We know that this proton is the experiencer. Let's use the experiencer equation here. For electric field, it's F over Q. We want to solve for force here. So let's rearrange this equation. It becomes Q times the electric field. That's 1.6 times 10 to the minus 19 times the field strength of 150 newtons per coulomb. That's going to give me 2.4 times 10 to the negative 17. 2.4 times 10 to the negative 17 newtons. Now, it doesn't ask us specifically what the direction of the force is, but force is a vector, so we really should have a direction in there. The field is pointing downwards. Which way is the force? Up away from the Earth or down toward the Earth? How do you know it's down toward the Earth? You're right. How do you know? Yeah. A proton will experience a force in the same direction as the field. If it was an electron or a negative particle, it would move opposite to the field, right? Positives with the field, opposites against the field. Field is downward, positive particle experiences a force with the field. So it's a downward field, it's a downward force. Now what about the gravitational force? We'll do the same basic thing. G is equal to F over M. That's my gravitational field equation for the experiencer. Rearrange that, it becomes M times G. That's 1.67 times 10 to the minus 27 kilograms, which is on your data sheet, times 9.80. Multiply those together, it's going to give me something like 1.6. Or is it 1.6 or 1.5? Times 10 to the minus 26. Should be 26, I think. Because we're multiplying 10 to the minus 27 by 10, basically, right? And that's a downward force as well. Gravity is the easy one, because gravity is always in the same direction as the field. The electric force isn't. It depends on whether it's a positive or negative. Good? Okay, the next question we wanted to go over was number 5. It says a metal box is charged by touching it with a negatively charged object. So we know that that metal box will become negatively charged. Right? It's charging by conduction, more specifically charging by contact. Negative touches neutral, they both become negative. They want to balance out, but depending upon the size and shape, they might not completely balance out. That's neither here nor there. It becomes negative. What does the charge distribution look like? Specifically, at the faces, right? This area right here versus the corners. What do we know about the charge distribution at the faces versus the corners? Yeah. Okay, they'll be evenly spaced here on the faces. What about at the corners? Yeah, so they're going to be closer together at the tips, right? So we're going to see them closer together here at the tips. If we draw the electric field lines for a second, it's going to look something like this. Field lines point towards the negatives, but in the corners, what do we notice about the field lines in the corners? They're closer together. And of course, the fact that those field lines are closer together in the corners tells us that the field strength is greater. We've just drawn the electric field lines outside the box. What about inside the box? Sorry? Yeah, there is electric field lines that we could draw inside the box, but they would all end up canceling each other out. So the easiest way to draw the electric field inside the box is to just leave it blank because they all cancel. Right? The net electric field inside a conductor is going to be zero. That's our Faraday cage, right? That we saw yesterday in a couple of videos. The airplane getting struck by lightning, and then there was the car getting struck by lightning as well. Next question, number 10. It says a uniform electric field. I'm going to underline that word uniform right now, okay? Because right away when I hear that, I start thinking parallel plates, E is equal to delta V over delta D. But we'll kind of read further on and see. Exists between two oppositely charged parallel plates connected to a 12-volt battery. That's my potential difference. The distance between the plates is 6.0 times 10 to the minus 4 meters. So that's delta D. What's the magnitude of the electric field between the plates? And I shouldn't have given you question B. Okay. That's kind of a hard question for you right now. After today, it won't be a hard question for you. That's a very doable question after today, but I just goofed and shouldn't have assigned that last night. The magnitude of the electric field between the plates. We know there's three electric field equations. The first one, which is the producer, the second one, which is the experiencer, the third one, the parallel plates. We know it's the last two that are applicable here. E is equal to F over Q, and E is equal to delta V over delta D. Now, F over Q is valid here whenever we have parallel plates, as long as we have an experiencer in between those plates. If we do have an experiencer in this case, we know nothing about it. So it's probably not going to be that middle equation we're going to use. Considering you take a look at the givens here, I think it seems pretty straightforward that these are the two givens. This is the equation we're going to use with these two givens. That's going to give me 2.0 times 10 to the 4. What would the units for that be? Yep. Good. Volts per meter or newtons per coulomb. We also have number 11 that we want to go over here. It says a metal car is charged by contact with a charged object. Compare the charge distribution on the outside and the inside of the metal car body. Why is this property useful to the occupants of the car if the car is struck by lightning? Okay, we're looking for a pretty short, quick answer to this question. Compare the charge distribution on the outside versus the charge distribution on the inside. On the outside, what are we going to find about the excess electrons? They go to the outer surface. Are they going to be evenly spaced? Not exactly, because it's not a perfectly uniform shape, right? But in most areas of cars, it's nice smooth curves, so you're going to find largely uniformly spaced charges, with some areas where there's a higher concentration than others. What are we going to find out about the charge distribution inside the car? On the inner surface of the metal. This is the easy one. There is none. There are no electrons on the inner surface of the car. Why is this useful to occupants if the car is struck by lightning? Well, because that creates an electric field inside the car that is equal to 0. And if there's no electric field inside the car, then you're perfectly fine. Finally, number 12. This is my favorite of the page. I'm glad somebody asked me to do it. Explain why only one of the electroscopes connected to the hollow conductive sphere in the illustration below indicates the presence of charge. So this one, we talked about the electroscope one day for a few minutes. Right? The leaves spread apart, that tells us the charge is present. It doesn't tell us what kind we have, positive or negative, but we know that charge is at least present. This one shows that there's a charge present. This one shows that there is no charge present. It's a difference. Why does this one show charge present, but this one not? Okay. Okay, so what's the difference between the outer surface and the inner surface then? Like, big deal. Good. So the electrons, the excess electrons are all going to go to the outer surface here, and they're going to be evenly spaced around the outer surface. Okay, that's going to create a a negative charge in this electroscope, which is going to cause the leaves to spread apart. Now, when connected to the inside, where there is no charge, because all the charges have been pushed to the outside, we have no electrons, no electric field, therefore these leaves won't be affected whatsoever. Good? All right, was that the last one? I think it was. We're going to go a step further here now, talk about electric potential energy and a couple more terms that are associated with electric potential energy. But first, before we do that, we're going to digress to physics 20, remind you of a couple of things that we learned about in physics 20. You guys know that in this unit, we've referred back to physics 20 and gravity a lot. First time was when we talked about the gravitational force compared to the electric force. Both inverse square relationships, right? F is equal to kq1 q2 over r squared, gm1 m2 over r squared. And then we talked about gravity when we talked about electric fields, the producer and the experiencer. Again, very analogous. Now we're going to talk about gravity in the context of energy. I've got a board marker in my pen, or my hand right now. Okay, I just set it on Kaylee's desk here. Relative to the desk, what's the pen's potential energy right now? 0, right? Relative to the desk. Relative to the floor, it's something. But relative to the desk, it's 0. Let's say I lift it from the desk to a higher point a couple meters up. Let's say its potential energy now is 8 joules. What's the change in potential energy between the desk and that point a couple meters up? 8 joules. How much work did I need to do? Think back to physics 20 now. How much work did I need to do in order to lift it from the desk to that height where it had 8 joules of potential energy? 8 joules. The work is equal to the change in potential energy that it experienced, right? Let's do it all relative to the floor. Let's say relative to the floor right now, its potential energy is 3. Okay? I lift it up. Now its potential energy relative to the floor is 9. What's the change in potential energy there? 6. How much work did I do in raising it from the desk to that spot? 6 joules. The work done against gravity is equal to the change in gravitational potential energy. That's not new. Okay, that's a physics 20 concept, absolutely. What do you think the next sentence I'm going to write down is, though? In an electric field. Good. Almost the same thing. In electricity, or in the electrical field, the work done against an electric field is equal to the change in electrical potential energy. And of course, the equation that describes that looks exactly the same. Delta EP is equal to W. In this case, it's delta EP gravitational, and in this case, it's delta EP electrical. You guys ever remember how we defined gravitational potential energy? Who remembers a pretty decent definition for gravitational potential energy? Kinetic energy was the energy of motion, right? Elastic potential energy was the energy that was stored in an elastic as it was stretched or compressed. Gravitational potential energy was the energy stored in a mass, due to its height, right, above a certain area, right, above the desk or above the ground, right? Make sense? That was a good definition for gravitational potential energy that we used in Physics 20. A very good definition, 99.999 whatever percent of the time. But it's not completely correct. It's a definition that worked in every context that we did because of that context. But it's not the true definition. The true definition of gravitational potential energy is the energy stored in a system of masses, not in a mass, not in a single mass, but in a system of masses a certain distance apart. In other words, we define gravitational potential energy of the pen relative to the ground. What we really, by rights, should have done is define gravitational potential energy of the system, of the pen and the Earth, when they're a certain distance apart. Now, why didn't we? Why did we talk about it just in the context of the pen and not the Earth? Yep. Yeah, the pen has almost no effect on the Earth. The pen is so light, the Earth is so heavy, that which one's going to move? It's going to be the pen, right? The Earth moves the tiniest little immeasurable amount. So for all intents and purposes, gravitational potential energy, its definition of the energy stored in a single object a certain distance above the Earth, worked just fine. We're not going to really change that definition because it still works for us. But understand that strictly speaking, it should have been the energy stored in the system of the two masses. Now, when we're talking about electricity, the magnitudes of the charges are likely going to be much more similar than the magnitudes of the masses in the example that I just gave you. Therefore, we can't abbreviate that definition like we did for gravity. We can't say it's the energy stored in a charge above a certain charge. Okay, when we're talking about electric potential energy, it's going to be the energy stored in the system of two charges a certain distance apart. Just like gravity really should be the energy stored in the system of two masses a certain distance apart. We could shorten the definition, simplify the definition for gravitational potential energy, and it works fine in almost every single case. But we can't do that for electricity, at least not usually. So we're going to leave it in the long form for electricity. I now have for you what might be perhaps the easiest physics problem that you have or ever will see. It says, moving a small charge from one position in an electric field to another requires this much work. What's the change in potential energy? Well, this is a hard question if you don't remember that work is the same thing as change in potential energy. But if you remember that work and change in potential are the same thing, then the change in potential energy, or the potential energy gained here, is simply going to be 3.2 times 10 to the minus 19 joules. Good? Okay, the key to that question clearly is remembering that work and change in potential energy are the same thing. If you do, it's easy, like easier than anything you've done. If you don't, well then, it's not easy. Let's give you about 30 seconds to answer these questions. Let's cover up those answers because I wouldn't want you to cheat and see them in advance. All right, you've had a chance to look at those now. Let me bring up the answers here. Any surprises? The second one you do have to do a little bit to, right? Because the work is equal to the change in potential energy. It's not equal to this. It's not equal to this. It's equal to the difference between the two, the change in potential energy. You know what I find funny about this textbook? Overall, it's pretty good. It's decent. But you know what? They always give us an example problem with every topic we do, right? Sometimes a couple example problems, sometimes 2 or 3 example problems, right? It seems to be, you know, look, when we have a nice easy topic, they give us an example problem. When we have a tougher problem or tougher type of concept, they give us a couple examples to kind of work through. Okay? For this one, I guess they must think this is a really crazy hard concept because they give us another example. Let's see if we can manage this one. When a small positive charge moves from a negative plate to a positive, this much work is done. How much potential energy will it gain? Well, if the work is 2.3 times 10 to the minus 19 joules, then so is the change in energy, the energy that's gained. It's the same thing. I'm not sure why they give us 2 there. I put them both up there because they give us both of them, but in the end, I think if you can do one, I think you can do them all. Let's give you about 8 seconds to do this one. Charge gains this much potential energy. How much work was done? 4.0 times 10 to the 5 joules. Good. Are you going to get a question that's just simple on a diploma exam?
No. That would be
Likely not, but I wouldn't say it's impossible. If you do get a question like this, a lot of you are going to get it wrong because you're going to think it's too easy, and you're going to try to make it harder than it has to be. If you remember the definition of work, the change in potential energy there, you should be able to get this question. Don't second guess yourself. Okay, now, are you likely to see something that's this straightforward? No, I don't think so, but it is possible. If you do, don't get it wrong. I think if you see this, you're more likely to see it as part of a larger question. So you need to do something with the work, but you're not given the work, you're given the change of potential energy. So you have to recognize what we've just seen, that the two are the same thing, but then use that number later on for something. Chad?
So where do you find the change of potential?
Well, work is change in energy, but the work done against gravity or against an electric field is equal to the change of potential energy.
So when you say against gravity or against electric field, it has to be gaining.
Well, no, not necessarily. Actually, could be losing. Okay, but we probably wouldn't say against. We'd say with. In that case, but that would still be work. Yeah. Maybe not even with, but maybe by the work done by gravity or the work done by the electric field, as opposed to against it. Yeah. But it would be the same number. It would just be a negative sign or a positive sign. Right? Now it starts getting a tiny bit harder, but still not that bad. You guys remember that W is equal to F times D, right? In fact, if I had have asked you here 20 minutes ago what work was, lots of you probably would have said, oh, it's F times D. You probably would have given me the equation that you used 100 times in Physics 20. Well, it still is. And it's still equal to the change of potential energy. Now all we have is an additional term here together. Work is equal to F times D. Work is equal to delta E. Therefore, delta E can also be equal to F times D. Questions aren't really any harder. It just involves a simple multiplication instead of just writing down the number that you're given. Let's define another term. Electric potential energy is the energy stored in a system of two charges a certain distance apart. Electric potential sounds almost exactly the same, but it isn't. Electric potential is the amount of energy per unit charge, not the total amount of energy that you have. That's electric potential energy. The amount of energy that you have per charge, that's potential. So we'll use an analogy here. Let's say there's 30 of us in this room right now. Let's say total we have $120. The amount of money that we have, the total amount of money that we have is $120. The amount of money per person that we have is $4. Right? It's $120, the total, divided by the number of people, 30. Gives me $4 per person. That's analogous to potential. The potential energy was the 120. The potential is the 4. The amount of money or the amount of energy per person. Okay? So energy is E. Potential is capital V, and it's the amount of energy per coulomb of charge. So to find that, we're going to go straight back to the definition. Energy per coulomb of charge, energy divided by charge. What do you think the units for electric potential are going to be? Joules per coulomb, right? Energy per coulomb of charge, joules per coulomb. But there is a way to abbreviate that. There is a way to shorten joules per coulomb into a volt. 1 joule per coulomb is the same as 1 volt. It's exactly the same thing. So we've got electric potential energy, the energy stored in the system of two charges a certain distance apart. We've got electric potential. It's that energy that we just talked about per coulomb of charge. So the energy divided by the charge. Here's another one. Potential difference. If potential energy is the energy that's stored in a system of two charges, and potential is the energy per coulomb of charge, then potential difference would be the change or the difference in potential. In other words, it would be the difference in the amount of energy per coulomb of charge. Now, there's two ways that we can find that. One is the easy way. Unfortunately, it doesn't appear on our data sheet, but don't think it's rocket science. You want to find delta V, the potential difference. It's going to be the final minus the initial potential. Potential difference, by the way, is the term that we saw the other day when we looked at parallel plates, right? Delta V over delta D. And I said, look, I'll kind of briefly explain what it is, and then we'll talk about it more in a couple of days. Today's that day. It's the difference in energy per coulomb of charge, or you could say it's the difference in electric potential between two spots. So there's one way to find it. That way is not on our data sheet. The second way is. The second way says delta V is equal to, well, V is equal to E over Q, and delta V is going to be equal to delta E over Q, the change in energy per coulomb of charge. What units do you think you want to use for this one? Delta E over Q is joules per coulomb, or you could say it's a volt, right? Joules per coulomb or volts. One more term now. This will be the last one for today, an electron volt. Let me ask a couple questions before we define this electron volt. What's the standard unit that we use to measure speed? Meters per second. Now, are there any other units that we can use to measure speed as well? Sure, like what? Kilometers per hour? No, not light years. Kilometers per hour, miles per hour, right? It could be kilometers per minute or meters per minute. Kilometers per microsecond. Sure. I mean, there's lots of sets of units that we can use, right? Meters per second is the standard units, but sometimes it's convenient to use a unit that's not the standard unit. What about distance? We've got meters, right? That's the standard units, but what else do we have? Kilometers, we have light years, okay, miles, inches, feet, okay? Okay, there's a million different sets of units that we can use for distance. The standard unit is the meter, but there's also other sets we can use if it's convenient. What's the unit that we use to measure energy? The standard unit for energy is joules. Well, sometimes it's not convenient to use joules. Sometimes we want to use a kilowatt hour. Okay, if you're measuring electrical energy, the power that comes into our house, the energy that comes into our house electrically, it's going to be a kilowatt hour. Another set of units that's used for energy is an electron volt. An electron volt is to joules as a light year is to meters, right? It's just another set of units that measures the same thing. It's just a matter of maybe sometimes it's more convenient because of context. Now, how do we define an electron volt? It is a unit of energy, but it's got to have a number associated with it. It is the energy that is gained or lost by an electron as it moves through a potential difference of 1 volt. Just like the pen, when I raise it up into the air, gains or loses potential energy. Okay, an electron gains or loses potential energy as I move it through an electric field, the potential difference. The amount that it gains or loses is equal to 1 electron volt. So what's the number actually? What's the conversion factor? Well, we're going to say delta V is equal to delta E over Q. We're going to rearrange that. We're going to say delta E is equal to Q times delta V. The charge here of the electron is 1.6 times 10 to the minus 19 coulombs. The potential difference here is 1 volt. That means the energy that is gained or lost, depending upon which way it's going, as the electron accelerates to a potential difference of 1 volt, is 1.60 times 10 to the minus 19 joules. Therefore, 1 electron volt is equal to 1.60 times 10 to the minus 19 joules. You don't need to remember that number. It's on your data sheet. Left-hand side of your data sheet, look for electron volt. It should say 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. So what if we have to do a conversion here? In fact, we will at some point soon have to do a conversion from electron volts to joules or from joules to electron volts. We know from our data sheet that 1 electron volt is equal to 1.60 times 10 to the minus 19 joules. Sorry. If you want to convert, let's say, 10 electron volts to joules, then here's how we're going to do it. We're going to set up a little ratio. 1 electron volt is equal to 1.6 times 10 to the minus 19 joules. We're told that on our data sheet. We're just kind of reformatting that, right? 1 over 1.6 is equal to 10 electron volts over x joules. We would take the x up by multiplying. We'd take the 1.6 up by multiplying. And we'd end up getting x is equal to 10 times 1.6 times 10 to the minus 19. Gives me 1.6 times 10 to the minus 18 joules. So if you want to convert joules to electron volts, you set it up as 1 over 1.6 equals 10 over x. If you wanted to convert joules to electron volts, then we just put the x on the top instead, right? It would be 1 over 1.6 equals x over however many joules you had. Now, some of you are just going to remember, oh, okay, I multiply when I'm trying to convert electron volts to joules. I divide when I'm going the other way around. If you can remember that, that's fine. Okay, the problem with that is, what if you don't remember it? What if you get them mixed up? Do I multiply or do I divide? Okay, this way always works. Works with other unit conversions as well, but works particularly well with this one. Okay, let's do an example here. I've got 2 examples and then we're done for the day. Moving a small charge of 1.6 times 10 to the minus 19 coulombs between positive plates increases the potential energy by this value. What's the potential difference between those plates? We're looking for delta V, not delta E, not potential energy difference, potential difference. We've got the potential energy difference, delta E. That's how much the electric potential energy is increased by. And we've got Q. So let's say delta V is equal to delta E over Q. 3.2 times 10 to the minus 16 joules divided by 1.6 times 10 to the minus 19 coulombs. That's going to give me 2.0 times 10 to the 3. And what are the units for that? Volts, or we could say joules per coulomb. Either one of those works, right? That one's easy enough, right? It's easy enough if you remember what all the terms are, right? If you remember the difference between potential difference and potential energy difference and so on, then it's easy. If you don't remember the differences, then it's not so easy. Let's try these 2 questions, okay? All right, if we're having no issues with these, let's do our last question for the day. This one's got a diagram, so it kind of looks a little bit more tricky, but in the end, it doesn't have to hurt us. Okay, if anything, a diagram should be able to help us out a little bit. It says moving a small charge of 3.2 times 10 to the minus 19 coulombs between 2 parallel plates from a position where this is my initial potential, not potential energy, but potential, to this place which is my final potential, capital VI, capital VF, and we were looking for, it doesn't tell us right here because I forgot to copy that over, but I believe we were looking for the potential difference. And in question B, I believe we were looking for the potential energy difference. So the energy that was gained as it did this. Okay? So if you look back at page 566, I think you'll find 2 parts to it. One where you're looking for the potential difference, and one for the potential energy difference or the potential energy gain. Want to find the potential difference? This is a pretty straightforward one, right? Delta V is equal to VF minus VI. VF is 4 times 10 to the 3. Subtract 2 times 10 to the 3. Gives us a value of 2.0 times 10 to the 3 volts. So the easiest way to find potential difference is to subtract the 2. If you don't have that, then try your other equation, V is equal to delta E over Q. Now we want to find potential energy change. Let's say now delta V is equal to delta E over Q. Let's use my other equation, but let's rearrange it. I get delta E is equal to Q times delta V. Q is 3.2 times 10 to the minus 19 coulombs times the potential difference of 2 times 10 to the 3 volts. Not 2 times 10 to the 3 because that's that value right there. It's 2 times 10 to the 3 because that's my difference. Multiply those together, guys, we're going to get 6.4 times 10 to the minus 16. And that would be in joules. 6.4 times 10 to the minus 16 joules. No direction, no direction. Energy is a scalar, right, Braden? Now, if you were looking for this value in electron volts, which we're not asked for here, but if we were, then we would say 1 electron volt over 1.6 times 10 to the minus 19 joules equals x electron volts over 6.4 times 10 to the minus 16 joules. The 6.4 goes up by multiplying, and I end up getting 4 times 4.0 times 10 to the 3 electron volts. So it's 6.4 times 10 to the negative 16 joules, or 4,000 electron volts. Now I want to point something out here, okay? Besides what you see up on the board. I told you back when we looked at electric field for the first time last week to always make sure you put the arrow sign over top of the E to not get electric field and energy mixed up. And I told you you wouldn't get the two mixed up the next day or the next day after that. But I told you at some point you would mix up energy and electric field. This is the first place where it would be really easy to mix them up. Okay, what if, in this question, we're not asked this, but what if we were asked for the electric field between these plates? Okay, electric field is E is equal to delta V over delta D. We have the potential difference between the plates. We don't have the distance, but you can imagine we could be given the distance in another problem, right? You can see that electric field, with the arrow over top of it, is closely related to the potential difference. So is change in potential energy closely related to potential difference. Okay, this is the first place where it becomes fairly easy to mix the two up. Okay, so I'm going to reiterate. Make sure when you're doing electric field, put the vector sign over it. When you're doing energy, don't put the vector sign over it. Don't get the two mixed up. Okay? These two things, although they look real similar, even the equations look pretty similar, are completely different things, completely different concepts. Okay, so keep that convention. Hopefully you won't make a mistake. Got a couple of questions for homework. We got about 8 minutes to do it, so hopefully you can get these done and not have any homework for tomorrow. Questions I want you to do are on page 566, please, 1 and 2.